Looking at an EDTA titration curve, it's going to look very similar to what we've seen with precipitation titration curves and with acid-base titration curves. The y-axis here is, instead of pH, like we do for acid-base titration, is PM, meaning negative log of the metal ion concentration. So that's our y-axis here. So this will always start at a low value because we have a high concentration of metal initially, because that's what we're titrating. So this will start low. It will slowly increase as EDTA is added and the EDTA starts complexing with the metal. And then as we approach the equivalence point, we get a very sharp change, and then it becomes a very high value, meaning most of the metal is complexed, and only a very small amount, so some of what we calculated in the previous video, is left behind. Now I've got a better drawing over here, not a drawing, but an actual chart, showing there's sort of three regions that we care about in this titration curve, and how we calculate it depends on which region we're in. So the first region is where we just have excess metal ion. We add EDTA, it reacts with some of the metal, but most of the metal is left behind unreacted. And so we don't need to worry necessarily about the equilibrium involving the complex. It's just that there's going to be a excess of the metal left over. Region 2, at the equivalence point, all of our EDTA, or we've added enough EDTA to complex with all the metal ions, and so there will only be a small amount left that's not going to be complex based on the equilibrium properties of the metal. So that's region 2. And then region 3, we have excess EDTA, which will complex with all of the metal ions that are left over. And so then we can figure out from that how much, what the concentration of the free metal ions are that's left in solution, which we need to calculate PM. Okay, and so in the next few videos, we're going to look at these three different regions for a particular titration. We're going to stick with calcium as our example here. Calcium is something you can titrate with EDTA. In fact, I've had students do it in milk, so that's been fun to see. But anyway, the titration we're going to be looking at is our analyte is 50 milliliters common volume for a titration of 0.040 molar calcium ion, and that's going to be and our titrant will be 0.080 molar EDTA. And we're going to look at, and the other thing we need to know, of course, is what's the pH, because that will affect all the equilibria. A common pH that EDTA titrations are done at is pH 10. And so from this, we can calculate the equivalence point. You can double check my work here. This is a one-to-one stoichiometry. The equivalence point should occur at 25 milliliters. Okay, so in the next video, we'll look at the region 1, where there's excess metal ion. The video after, we'll look at the equivalence point, and the final video, we'll look at where there's excess EDTA.